this recording. Okay. Now, last time we started with the matrices. Remember what's a matrix? Let me just remind you. A matrix, so when F is a field, usually F is real numbers or complex numbers. Then a matrix is something like this: A11, A1n, and AN1, AM1, and AMN. So it's a bunch of numbers, scalars, but formally it was, remember, it was formally a function from some set. Sorry, this is function from some set ij, where I runs from 1 through m, and j runs from 1 through n. And in the F11 is a first entry, etc. So that was the function. Can you turn off? Hey, can you turn off your microphone, please? Where is it? Please turn off all your microphones. Okay. Okay, let's when we have a matrix, we may write it like this: Aij, and we define scalar multiplication as where C is a, let's say, a real number, or from the field. Field, as I said, as we said, it can be either real number or complex numbers. This is the ij entry of this matrix is C times Aij. We just defined above. So that, let me give an example. Example, if you have 2 times a matrix, let's say 1, 2, 3, 4, 0, 5, for example, you multiply each entry by 2. It's 2, 4, 6, 8, 0, 10. So it's a function when you, if you, in order to multiply a function by 2, you just multiply each value by 2. Yeah, that's a function. Now, this is scalar multiplication. We also talk about the addition. For example, 2 times 1, 2, 3, 4, 0, 5 plus minus 3 times, let's say 1, 1, 1, 2, 2, 2, for example. This is, or this is, you may write it minus 3. It is 2, 4, 6, 8, 0, 10 plus. In order to add 2 matrices, they have to be the same size, of course, otherwise you cannot add them up. So namely, in order to add 2 functions in general, their domains must be the same. Their domains must be the same. So that minus 3, sorry, minus 3, and minus 6, minus 6, minus 6. And when you add them up, it is minus 1, plus 1, 3, 2, minus 6, and 4, for example. This is easy task. Our main purpose for matrices is that the main objective of this course is to be able to solve systems of linear equations. And in order to solve the systems of linear equations, we need these matrices. Okay, let's see. And here's a theorem that you can show it easily. So suppose that addition and suppose that you can let A, B, and M cross and matrix. Then if you not A1 and A2, A1, let me add here also A1, A2 also. Let's say we have P, B, 3 matrices. more precisely. Yeah. Let A1, A2 be 3 M cross N matrices. Okay, then we have C time, and C is a constant or scalar. A1 plus A2 is C times A1 plus C times A2, just like as in the real number case. But these are A1 and A2 are not real numbers, but are matrices. And you can have a matrix, and you can multiply. First, you may add two numbers and then multiply by a matrix. It's the same thing as you multiply first the matrix by the first number plus by the second scalar and add them up. Or you may multiply first two numbers, scalars, and then by matrix. It's the same thing as you first multiply by C2 times A, whoops, not A2. This is the bad side of using tablet. You have to change it to eraser. Anyway, and you multiply by C1. Okay, it's the same thing. And if you multiply a matrix by 1, you multiply each entry by 1, the result is the same. And also, if we multiply by -1, this is just minus A, as we, minus A, remember, you multiply each entry by -1. Okay, so you can show them easily, which I will not do that. So this one non-trivial thing is the multiplication. Multiplication of matrices. Okay, let A, B, and M cross N matrix. So remember, M is the number of rows, and N is the number of columns, and B N cross R matrix. So that the number of columns of A is equal to the number of rows in B. Then the matrix, the multiplication. AB of the matrix AB, A and B. A and B is defined as follows. It's ijth entry. Ijth entry is the ijth entry of AB is, so AB, the matrix AB, its ijth entry is what? We may multiply AI K, B, K, J, and K runs from 1 through N. And for each ij, I is from 1 through M, and J is from 1 through R. So that, yeah. So for example, let me give an example. This is example. So if A is something like this, A1, let's write Aij. So let's look at the ith row. This is AI1, AI2, AI, and there's also other stuff here which I will not write, AIN, And the jth column of, this is the ith row, jth column of B is something like this: B1J, B2J, and B and J. There are N, and also there's some more stuff here. So what you do is, what do we do is that you multiply this these elements by those and add them up. That's the multiplication. Let's give some example. We will understand better with the example. If we have, let's say, 2, 3, minus 1, 0, 4, 2, for example, and this is the number of rows is 2, and the number of columns is 3. So we must have 3 columns here, and the rows might be arbitrary. Let's say 1, 1, 2, 2, 1, 3, 0, 1, 4. Let's say minus 1, minus 1, minus 1, for example, like this. Then the answer is, you multiply first. Sorry. What do we do? You multiply this first row by the first column of the second matrix. It is 2 times 1. Let me write one of this. 2 times 1 is 2. 3 times 1 is 3, is 5. Minus 2 is 3. And we multiply by the second column. By the second column, 2 times 2 is 4. Let's add 4 plus 3 minus 3 is 4, etc. And 3 minus 4 is minus 1. And minus 2 minus 3 is minus 5, plus 1 is minus 4. 4 plus 4 is 8. We multiply 0 by 1, 4 by 1, and 2 by 2. So that's 8. Add them up, of course. And then here we write 4 times 1 is 4, plus 6 is 10. 4 plus 8 is 12. Minus 4 plus minus 2 is minus 6. I hope it's right. Something like this. So that's the multiplication of these two matrices. And the formal definition is above. Okay. That's one example. So you may have another example. For example, let's see another example. Let's say 2, 3, 4, 1, and 1, 1, 1, 1, for example. Then the answer would be, this is think of this is 1 by 4 matrix, and the second one is 4 by 1 matrix, so that these entries are the same. So number of columns in the first matrix is equal to the number of rows in the second matrix. So the result will be a 1 by 1 matrix, which is 2 times 1 plus 3 times 1 plus 4 times 1 plus 1 times 1 is 5, 9, 10. So it is a 1 by 1 matrix. That's right. But if you multiply the other way, for example, 1, 1, 1, 1, and 2, 3, 4, 1, then the situation is completely different. So because 1 times 2 is 2, 1 times 3 is 3, 1 times 2, 4 is 4, 1. I wish I had chosen different numbers. Anyway, so it is 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1. So that is, so this is, if you call this matrix A, that matrix B, this is A times B, but this is B times A. In this case, it's possible, but in the above example, for example, in this example, here A times B is defined, but B times A is not defined. Here, BA is not defined. Okay, next. Even they are defined. Let me give one more example. Suppose they are defined. Let's say an easy example. Easiest example is, let's take A to be 1, 0, 0, 0, and B to be 0, 1, 0, 0. So this example will show you the difference between the multiplication of matrices and the multiplication of numbers, real numbers. Transpose. It says, what if n cross m and b is m cross n, whose transpose are n? No, usually they're not the same. You can check it. The answer is no, probably no. Okay. Or I'm not sure, but you should check it. Okay. I have to check it. So, but from the beginning, you cannot assume anything that a times b is equal to b times a. So in this example, a times b is 1, 0, 0, 0, 0, 1, 0, 0. That is 0, 1, 0, 0. But if you look at b times a, they're all 2 by 2 matrices, so both of them are defined. 0, 1, 0, 0. I hope I'm not writing too fast because I want this lecture to be just like in the class.
I think it's okay.
Okay, not too fast. You should be able to write your own notes as well so that you learn it.
Yes, I can write.
Okay, so if I'm fast, just let me know. Okay, 1, 0, 0, 0. If you multiply this, then the answer is 0, 0, 0, 0. So that a times b and b times a are defined, but AB is not equal to BA. So remember, if two matrices are the same, if each corresponding entries are the same. So for example, these two matrices A and B here are different matrices. Although their entries are the same in different places, but they are different matrices. A is not equal to B. The reason is that here in the first entry we have 1, but in B we have 0 in the first entry, so that they are different matrices. Okay, good. Next. About this theorem for the properties of multiplication, there is an easy proof that you can see that A times B times C is equal to A times B times C, although it is not, so it says it is not commutative. But it is associative. Just like the multiplication of in real numbers or complex numbers or addition, they satisfy this property. So the matrix multiplication also satisfies this property, the associativity. You can, if you look at the lecture, the textbook of Jamal Koch, you can see an easy proof of this in any linear algebra book, actually. You can check it. Well, of course, this is true whenever these multiplications are defined, so that when you write A, B, C for the multiplication, whenever this multiplications are defined, this makes sense. So why do we write this property? So because we want to be able to write this A times B times C times D, E, etc. So you can multiply in any order you like. So as long as you multiply a matrix by the next one. So you can multiply in any order. And the second property is, so this is the side, this makes sense. If you first add two matrices and multiply by A like this, it is A times B plus A times C. And also you can add first A and B and multiply by C. It's the same thing as A times C plus B times C. Next, remember this identity matrix of size n. So when you write like this, we are assuming that this multiplication is possible. If it is not possible, of course, it does make sense. Or A times identity is equal to A. Whenever these multiplications are possible. And if you multiply A times B by a constant C, is the same thing as C. You multiply A by C and then by B, or you multiply C by B by C and then multiply by A from this side. They are all the same. And yeah, that's the theorem. The proofs should be, only the first one is a little bit tricky, but not too difficult. You can find it. The others are easy. Okay, just from it follows from the definition. And so let A be an n cross n matrix. Namely, it's a square matrix. We call it square matrix. Namely, square matrix. Then we may define A times A, and we denote by that A square, and A cube is A times A times A. So remember, since by the first property above, this first property, very first property, the order is not important. You can multiply in any order you like, although all these matrices are the same. So you can either write this A squared times A or A times A squared. They're the same. Well, in general, A to the K is A times A times A. And it has this property that A to the K times A to the L is A to the K plus L. And A to the K, if you multiply A to the K, if you find this matrix and then raise to the nth power, it is A times KL, just like in the real numbers. Okay. Let's give some more example. One more example. So if we have, for example, 2, 1, 0, 1, 3, 2, 1, 1, 2, and minus 1, 2, so that this is 1 by 3, second one is 3 by 2, and the last one is 2 by 1 matrix. This is, for example, you can multiply this in any order you like. Let's multiply the first two matrices. It is 2 plus 2 plus 0 is 4. Oops. Yeah, 4. And 2 plus 3 is 6, plus 1 is 7. So this is 4, 7. And minus 1, 2. And the answer is minus 4 plus 14 is 10. Okay. So I multiply by A times B times C. You can also check the other way around. Okay, about the transpose. Now, yeah, we We will talk about the transpose. Remember what was transpose? Transpose of a matrix. You just A transpose, its ijth entry is the jith entry of A. So namely, if A is, let's see an example. Let's take 1, 3, 2, 1, 1, 2 in the above example. Then A transpose is 1, 2, 1, 3, 1, 2. You make rows column and columns rows. Okay. The properties of this transpose is that, let me write as a theorem, that A plus, if you add A and B and then take the transpose, it is the same thing as take the transpose and of each matrix and add them up. It's the same thing. Or take a matrix and multiply it by a constant C and then take the transpose. It's the same thing as taking the transpose of CA and multiplying by the constant. Meeting will add in 10 minutes. After that, let's give a 5-minute break and then we will continue. Okay, next. A, B transpose, if you multiply A times B and then take the transpose, it's the same thing as B transpose times A transpose. This makes sense because if A is an M cross N matrix and B is an N cross R matrix, then the multiplication A times B is an M cross R matrix, and its transpose is R cross M matrix, right? Its transpose is R cross M matrix. So this is an R cross M matrix, and this is B transpose is R times N matrix, and A transpose is M cross N cross M matrix. We just interchange these numbers so that their multiplication is an R cross M matrix. At least the sizes are the same. Sizes are the same, but in fact, they are the same matrices. You should, if you are confused, just give them or see them on an example. Just write a matrix A, matrix B, and multiply them, take the transpose, and look at the other side as well. So you should convince yourself like that on an example. And A transpose is the same thing as A. Namely, if you make rows column and columns row, and then if you do it once again, you get back to the original matrix. Okay. Now, so let's give some, maybe, let me give some example. So if A is, let's say 1, 2, 3, 4, then A transpose is 1, 2, 3, 4. Then if we take transpose once again, what do we get? 1, 3, 2, 4, and that is the matrix A. So this is not the proof, but this is just an illustration of the proof. Okay. Another example. Any questions so far? If you have any question, when I ask you, you may write there. Okay. Next, that's partition matrices. So suppose so somebody's microphone is open, on, so please turn it off. So suppose A, B, A1, A2, A3, A4, where these are A1, A2, A3, A4 are matrices. Yes, we follow, at least we follow the topics from the linear. This is a textbook of Jamal Koch, and you can see the syllabus on the OT class. The syllabus is OT class.
Hocam,
Yes.
do you have PDF file for Jamal Koch's book? Because
No,
I couldn't find it to buy.
No, I don't.
Oh, okay.
The book might be on the bookstore. I don't know. Maybe you can order from there. Maybe in our
Okay.
department. I'm not sure. I'm
Okay,
not sure.
thank you.
But I don't have the PDF file.
Okay.
Okay. If I find it, I will let you know.
Okay, thank you.
Okay. And suppose the matrix B is let's say B1, B2, B3, B4, B5, and B6. How do you multiply this? Where here, yes, I will upload this to a YouTube channel, but as I wrote to you there, I have some problem with my computer. So as soon as I can, I will upload this to the YouTube channel. I cannot put this on the OT class because there's already some lectures there, so I cannot upload there. Instead, I will upload this these in the YouTube channel, and I will let you know. But it will take some time. Okay, it will take some time. I don't know how much time, but I will try to do it as soon as possible. Okay, suppose then you can check that this A times B is A1 B1 plus A2 B4, and the second entry is A1 B2 plus A2 B5 and A1 B3 plus A2 B6 and A3 B1 plus A4 B4, A3 B2, oops, plus A4 B5, and finally A3 B3 plus A4 B6. So if, for example, A is a 2 by 2 matrix and B is a 2 by 3 matrix, these coefficients, this AIs and BIs are numbers and multiplications like this. But if these AIs and BIs are matrices, and if these multiplications are possible, still this product is true. So let me give one example of this. Let's look at this matrix A as 1, 2, 0, 1, 3, 1, 1, 2, 4. And and B is 1, 1, 1, 2, 4, 5, 3, 4, 0, minus 1, 2, 1. So if let's divide this into pieces like this. So that this matrix is A1, this is A2, A3, A4, this is B1, this is B2, B3, and B4. Just like in the above example, if you let's compute this. So A is A1, A2, A3, A4, and the B is B1, B2, B3, B4, we can multiply them just like AB as A1 times B1 plus A2 times B3, as long as this multiplication is possible. Here it is, in this example, it's possible A1 B2 plus, so let me write, not this is equal, but we will see that they are equal. A1 B2, A2 B4, and A3 B1 plus A4 B3, A3 B2 plus A4 B4. Let's compute these